Mixture separations using liquid-liquid extraction is of great importance in the petroleum refining industry. The figure here is a schematic showing a variety of applications of liquid-liquid extraction in petroleum refining. Most of these applications involve the separation of aromatics from hydrocarbon mixtures. For example, sulfalane extraction of the naphtha fraction for the 63 to 69 degrees centigrade boiling point range to produce food grade hexane. Extraction of aromatics such as benzene, toluene, and xylene from straight-run naphtha using sulfalane, TEG, tetraethylene glycol, NMP. Extraction of aromatics from straight-run kerosene fractions by a variety of solvents, including sulfalane, TEG, liquid sulfur dioxide, not used anymore, in order to produce aviation turbine fuel and to reduce the smoke point of kerosene. If we go on to the atmospheric residue, we have liquid-liquid extraction processes for producing lube oils with improved flow properties with high viscosity index, and the vacuum residue is subject to de-asphalting, which is a liquid-liquid extraction process to produce de-asphalted oil. And asphalt is the aromatic rich product that is used in construction of roads. Further details are available in my papers. The first one in Industrial Engineering Chemistry Research 2016 and Chemical Engineering Science 2019. Let us gain an understanding of the principles of liquid-liquid extraction by taking the specific example of extraction of toluene from mixtures with heptane using sulfalane as solvent. We plot the compositions of the three components in the mixtures in ternary composition space. The compositions are expressed in mole fractions. The mixture toluene sulfalane is completely miscible. The mixture toluene heptane is completely miscible. There is, however, a range of immiscibility within the binodal envelope marked green. The red line denotes the spinodal curve that delineates the region of phase stability. The area between the binodal and spinodal curve is a metastable region. This area here is also a metastable region. The area within the red colored envelope is an unstable region. Any mixture with a composition in this region will split into two phases. Let's consider a feed mixture of toluene and heptane from which we need to selectively extract the aromatic toluene. We bring this liquid mixture with this composition into contact with sulfonine, and with the proportion of sulfonine to hydrocarbon toluene mixture that is used, the mixture composition ends up at the position indicated by M. M lies within the unstable region and will separate into two liquid phases indicated by E and R. This E is the extract phase and R is the raffinate phase. The yellow line is the tie line. We will note that the extract phase is richer in the aromatic toluene than the feed mixture, and that is the principle of liquid extraction for extraction of aromatics. So in the sulfonine phase, the components will equilibrate from this point to this point here on bringing sulfonine in contact with the toluene heptane mixture. For the hydrocarbon mixture, the equilibration will follow this line indicated by the dotted line HT to the raffinate. We note that both extract and raffinate are on the boundary denoted by the binodal curve, and the equilibration trajectory indicated by the dotted lines remain in the homogeneous liquid phase, and no emulsion formation is to be anticipated because the equilibration trajectories do not enter the metastable region. Again, an understanding of the basic principles of liquid-liquid extraction, let's have a quick look at the hardware used in the petroleum industry. Basically, we have two types of contactors in which the two liquid phases, say the solvent phase, for example, sulfonine is brought into contact with the hydrocarbon mixture containing aromatics that needs to be extracted. The contacting can be in columns that are mechanically agitated. Since we desire high degrees of separations, the contacting is done in several stages, and a variety of equipment have been developed for liquid-liquid extraction processes. They include the old shoe Rushton column, the York Schiebel column, the rotating disc contactor or RDC, the Kearney column, the asymmetric rotating disc contactor. There's another class of contactors that are unagitated. There could be a spray column, but spray column will have a high degree of backmixing and not to be recommended for industrial applications unless the staging requirements are not severe, and a single well-mixed stage is sufficient for extraction purposes. We have a sieve tray column, very common in sulfonine extraction for, say, producing food-grade hexane. Several industrial units employ the sieve tray contactor, We have the packed columns for liquid-liquid contacting. The most common ones that I'm aware of are the RDCs in this category and the sieve tray columns in this category. I have a few remarks to make about the rotational speed used in the agitated columns. The rotational choice of the rotational speed is important because the number of rotations per second dictates the drop sizes. With increased rotational speed, the drops become smaller in size. Therefore, there is more area per unit volume. But on the other hand, smaller drops tend to be rigid and stagnant, whereas larger drops are more mobile and afford higher mass transfer coefficient. Consequently, increasing the rotation speed beyond a certain point may be counterproductive. Indeed, it is a part of common folklore within the petroleum refining industry that an RDC column works best when the agitator is switched off. I leave the discussions at that point and move on to the possibility of emulsification. Now, emulsion formation is detrimental to the operation of a liquid-liquid extraction column in industrial practice because phase separation would become problematic. We now discuss the possibility of spontaneous emulsification in liquid-liquid contacting. For illustration, let us consider a mixture of ethanol and benzene with composition denoted by this position B here, 50-50 mixture of ethanol and benzene. Let us bring that mixture into contact with pure water. The proportions of these two mixtures is such that the mixture composition ends up in the two-phase region indicated by the point M. The green line is the binodal curve, the red line is the spinodal curve, and the region between the binodal curve and spinodal curve is the metastable region. So when ethanol benzene mixture is brought into contact with water, the mixture will separate into two liquid phases with compositions denoted by A star and B star. These compositions, A star and B star, are at the ends of the tie line indicated by the pink line. Therefore, in the water-rich phase, the compositions will change from A to A star because A star is the equilibrium composition, and in the ethanol benzene rich phase, the compositions will equilibrate from B to B star, where B star is on the tie line. Now, the equilibration trajectory B star remains in the homogeneous region and no emulsion formation can occur. However, we note that in the water-rich phase, the equilibration trajectory lies within the metastable region between the red colored spinodal curve and the blue colored binodal curve. By definition, the entry into the metastable region could result in emulsion formation, and we will have the formation of oil drops in water, and this occurrence of oil drops in water is a spontaneous process driven by the driving force due to the chemical potential differences between A star and B. So the approach to equilibrium results in spontaneous emulsion formation without expenditure of energy. Further details on the calculations to determine the binodal curve, spinodal curve, the definitions of thermodynamic equilibrium, equality of chemical potentials are available in my papers listed here. Watch also my presentations on the Ouzo effect, diffusion and liquid mixtures, and uphill diffusion on my YouTube channel. Indeed, the Ouzo effect is another example of spontaneous emulsification that results when we add Ouzo, which is an aniseed-based liqueur, to water. But the details are in my video presentation on the Ouzo effect. Note here that the equilibration trajectory is linear in both phases. Let's expand on that a little bit in the next slide. Let's move on to a different system consisting of a mixture of water, dimethyl sulfoxide, also called DMSO, and tetrahydrofuran. The binodal curve is indicated by the green line. The spinodal curve is the red line. So the unstable region is within the spinodal envelope. Let's take a mixture with composition denoted by this point and bring that mixture into contact with water. If we examine the mixture composition, which is here, the mixture composition is in the homogeneous region. We would, if the equilibration trajectory were to follow a straight line path, no emulsion forming would result. However, if we calculate the equilibration trajectory taking due account of diffusional coupling effects described by the Maxwell-Stefan diffusion formulation, the equilibration trajectory follows a curvilinear path indicated by the solid black line. And we note that the solid black line has exhibited a foray into the metastable region, leading to emulsification. Therefore, curvilinear trajectories engendered by diffusional coupling effects may exhibit forays into metastable regions, leading to emulsion forming. The need for the Maxwell-Stefan diffusion formulation is discussed in detail in my papers here. See also my presentations on diffusion in liquid mixtures and uphill diffusion on my YouTube channel. These describe the use of the Maxwell-Stefan diffusion formulations to model equilibration trajectories in liquid mixtures.